Okay, we've been talking about directions, we talked about points, now we're going to talk about planes. And we're going to stop here. I promise there's not any crystallographic volume, it's just planes. So first off, we're going to need an algorithm. You know, you're like, well, what, an algorithm? Is this programming? It's not, it's just, if you don't like algorithm, you can say a method for determining the Miller indices of a plane. And Miller is just the guy who came up with this idea, so that's why his name is attached to it. And it's just, once again, having some numbers that we can use so we can talk about any particular atom, even with a different crystal structure, in the same terminology. Okay? In the same terminology. So the first part is you have to find an origin. You find an origin to begin calculating this. And if the plane you're looking at or caring about passes through the origin that you selected originally, you gotta get a new origin. The plane can't pass through it because of how we define it. So just pick a different corner of your unit cell, you'll be fine. So you know, if this is your unit cell, we're looking at a plane, and this is where you said your origin was, and then you choose this is the plane. You can't do it. Pick any of the other corners. This corner's fine, that corner's fine, that corner's fine. This other corner back here that you can't see would be fine. Any one of them will be fine. Okay, now you have to look at where that plane intercepts the axes. It's always in terms of A, B, and C. So, for this example right here, if this is my origin, and I do everything like normal, that's the Y direction, this is the X direction, this is the Z direction, okay? Well, where does it intersect? Well, it intersects the X-axis at one length, so that'd be A, and it never intersects the Z or the Y-axis, which you might be like, well, what do I do then? Is it 0? If it never intersects, then you have to remember that technically parallel lines intersect at infinity. This is this weird geometry thing, so you would just put infinity for these two. And then luckily, to make things less weird, take reciprocals of those intercepts. So what you thought was going to be crazy within two infinities becomes 0. 1 divided by infinity is 0. So you would have 1 over a, 0, 0. And it's like last time, we multiplied by our last parameters, so the length of each side. So I get 1, 0, 0 for this plane. And then the last thing will be I'd enclose it in commas. Or sorry, in parentheses with no commas. Goodness. So that's my method. So let's try an example problem here. Okay, I have a plane. The only corners I can't choose as an origin are here, 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 or here. Those 4 will not work. Everyone else is free game. I'm going to just choose where the origin is currently because that works. Okay, then in mind we have to figure out where does it intercept each axis. Well, it intercepts at a length A, because that's where it hits the x-axis, and a length b on the y-axis, and a length infinity on the c-axis because it doesn't ever intersect. I invert those, so 1 over a, 1 over b, and 1 over infinity, which becomes 0. 1 over infinity is always 0. Anything divided by infinity is usually 0. If you got infinity divided by infinity, that's where things get really wonky and weird. And then you normalize them. So I multiply each of them by their respective things. So A I multiply by A, B by B, and C by C. And I get 1, 1, 0. Finally, I put those in parentheses. Now, this whole reduction thing is simply saying that if I have like 4, 2, 0, I can divide everything by 2 to get down to 2, 1, 0. I want the smallest integer. The smallest integer there. And finally, I put it in parentheses, and we're good. So that's it for this time. Next time I'll do a couple more practice problems on this. So I hope this helped you. Thanks for listening. See y'all soon. Bye-bye.